My name is Maitreyi Marathe. I'm a PhD student in electrical and computer engineering at the University of Wisconsin-Madison, advised by Professor Lena Roy. Today, I will be talking about our work on using mathematical optimization for home energy management for prepaid electricity customers. Prepaid electricity is pay-as-you-go electricity. So you buy credit before you can use electricity, as against the more common postpaid option, where you get a bill at the end of the month for what you have already consumed. There are estimated to be about 2.5 million prepaid electricity customers in the United States and about 11 million in the United Kingdom. Prepaid programs are popular among low-income customers because they do not need to pay deposits or go through credit checks. There is also no bad debt for the utility. However, when the prepaid wallet balance hits zero, the customer is automatically disconnected. These unanticipated disconnections can be dangerous, particularly during extreme weather events. There can also be a high fee associated with getting reconnected. Additionally, low-income customers experience what is called the heat or eat problem. They have to decide how to use their limited disposable income. They can either choose to forego critical needs like food in order to run their air conditioner and other appliances and have enough money to pay their energy bills, or they have to forego using some electrical appliances in order to pay for food. Such households have to actively decide what appliances to use and forego so that their energy bill is within an affordable limit. And so a framework for effective energy rationing is necessary. The contribution of our work is an energy rationing framework for prepaid customers. It prevents disconnections and extends the use of critical appliances by managing discretionary appliances. Let me explain this through an example. I'm sure at some point your phone may have given you a notification that your battery has reached 20% state of charge and it has switched on the low power mode. In the low power mode, your phone reduces non-essential services in order to preserve juice for important features like texting and calling. Our framework does something very similar. It assumes that the prepaid wallet is like a battery in terms of money. Consider this simple example where we have three appliances. The framework assigns a threshold to each appliance. The TV is assigned $20, the lights $10, and the fridge $1. As the user uses appliances, the wallet balance drops. When the balance drops below the threshold assigned to a load, the load is disabled. So initially, all three loads are enabled. Then the TV is disabled, since the balance drops below $20. Then the lights are disabled. And finally, all loads are disabled to prevent a disconnection. Our optimization model takes as inputs the demand forecast and the user-defined priority order for appliances, and it generates thresholds for each appliance. Here we present results from a case study using real-life energy usage data for a month. On the x-axis, we have the ratio of the energy that the customer can pay for to the energy that the customer wants. So towards the left of the x-axis, we have poorer households, and to the right, we have households that can afford to pay for 100% of their energy demand. On the y-axis, we have the percentage of time for which appliances are available to be used when needed. We compare the performance of our model that generates optimized thresholds to a baseline case with no energy management and a case with fixed thresholds based on heuristics. We see that our model performs better than the other two and has more improvement, particularly for poorer households. It also prevents the wallet balance from reaching zero, thereby preventing the inconvenience and fees associated with a disconnection. The model can be implemented on a remote server, and thresholds need to be communicated only once a day to the end user. Utilities generally give prepaid customers in-home displays that already calculate the wallet balance, so additional in-home hardware may not be required for implementing our framework. In conclusion, we have presented an energy rationing framework for prepaid electricity customers. It is a simple tool with minimal requirements in terms of in-home hardware and remote communication. It can be extended to other customers, such as those on energy assistance programs or even pay-as-you-go solar home system users in developing economies. We have assumed perfect information about demand forecasts, and we are currently working on studying the effects of imperfect demand forecasts on our framework. If you have any questions or want to know more details about the optimization formulation, please feel free to reach out. Thanks so much for listening.